All right, hello to chapter 2 of the Introduction to Quantum Mechanics. We're reading section 2.3 today, the harmonic oscillator. The harmonic oscillator is split up into two sections. Point 1, which is the algebraic method, and then point 2, which is the analytic method. I'm wondering if I should do this in two sections because both of them are pretty thick. So this may be part 1, which is just the first section. Let's read the introduction. The paradigm for a classical harmonic oscillator is a mass m attached to a spring of force constant k. The motion is governed by Hooke's law. Here we have Hooke's law. F is the force, negative k, the k constant, x is the separation of the oscillator in position. This equals to m, second derivative of the position with respect to time. So this is just Newton's law. Right, F equals ma here, and then this is Hooke's law in the middle. Ignoring friction. And the solution is a summation of sine and cosine waves. Very interesting because we have a differential equation here, very similar to the one we saw with the infinite square well. This gives us general solution, summation of sines and cosines, where omega, the frequency, is the Hooke's constant, or sorry, the spring force constant, k over the mass m, square root of all of that, is the angular frequency of oscillation. So this is the angular frequency of oscillation. The potential energy is 1/2 kx squared. Nice. So this is the potential that we're going to put in the time-independent Schrodinger equation. It is a parabola. Of course, there's no such thing as a perfect harmonic oscillator. If you stretch it too far, the spring is going to break, and typically Hooke's law fails long before that point is reached. But practically, and any potential is approximately parabolic in the neighborhood of a local minima, figure 2.4. So right here, the local minima, this can be approximated by the harmonic oscillator potential, which is right here, x proportional to x squared, parabola. In the neighborhood of the local minima, okay? Formally, if we expand v of x in Taylor series about the minimum. So this is a Taylor series expansion. If you don't know what this is, we got to do a little bit of Taylor series. I think when you first learn this is in calculus class, some trigonometry. You know, you want to approximate a cosine function, so you use Taylor series, but that's okay. So the first term is v taken at this x value. The second term is the derivative of v taken at this x value and x minus this minimum value. And then the second term is 1/2 second derivative of v times the squared term, and so on and so forth. There is a equation that gives you Taylor series expansion. For now, don't worry about it, just take it as a given. So they approximate it here as the second term only, which describes simple harmonic oscillator about the point x of 0. Interesting. Why do they approximate it there? So it looks like they remove this, they remove this, and they just keep this. You see that term there? This is the only term they keep. I'm assuming they keep this because if x is 0 here, then this is 0. So if you expand about the minimum point and the minimum point is 0, this term is 0 and this term is 0, but this term is non-zero. Is that true? I'm not sure. We're going to keep reading. About the point x0, with an effective spring constant, k is equal to the second derivative of the potential v at this point x0. That's why the simple harmonic oscillator is so important. Virtually any oscillatory motion is approximately simple harmonic, as long as the amplitude is small. Number 22. The quantum problem is to solve the Schrodinger equation for the potential, boom, and here they give us a modified potential. 1/2 m, the mass, omega squared, the resonant frequency, or the frequency of oscillation, and x squared. It is customary to eliminate the spring constant in favor of the classical frequency using equation 2.42. Okay, so we remove the spring constant and we use this guy only. As we have seen, it suffices to solve the time-independent Schrodinger equation. So here's the problem set up. Time-independent Schrodinger equation. In the previous problem, we solved this equation, except here we had the potential of the infinite square well, which was 0, or infinity at the boundaries. In this case, it is a non-zero potential, so we have to solve a new differential equation. In the literature, you will find two entirely different approaches to this problem. the problem of solving this equation. The first is a straightforward brute force solution to the differential equation using the power series method. It has the virtue that the same strategy can be applied to many other potentials. In fact, we'll use it in chapter 4 to treat the hydrogen atom. The second is a diabolically clever algebraic technique using so-called ladder operators. I'll show you the algebraic method first, so the ladder operators, because it is quicker and simpler and a lot more fun. If you want to skip to the power series method for now, that's fine, but you should certainly plan to study it at some point. So here's the two methods. First is the algebraic method, which introduces the ladder operators. This is a method of solving this equation over here. The harmonic oscillator potential of the time-independent Schrodinger equation. The second method is a power series-based method, which is called the analytic method, which we're going to see in the next section. So right now, we're going to cover this method. Let's peep what they do. And keep in mind, he calls us diabolically clever. Very cool. To begin with, let's rewrite equation 2.45 in a more suggestive form. Equation 2.45 is rewritten in this manner. How is this rewritten? Well, the E stays the same. E stays the same. But here we do some manipulation. 2m gets pulled out from here. There's a 2 and an m here, but there's an extra m being added here. All of this becomes squared because we pulled out an extra m, so there's an m squared there. This 2 gets pulled out in the front here, and this 2 gets pulled out, which leaves us with minus h squared, derivative with respect to x, the second order derivative of this, which we can replace with the momentum operator. Okay, I think the momentum operator has an I in there, but since we have a negative sign and a negative sign there, the I gets removed. Looks good. Okay, if this was confusing, don't stress. Just keep in mind we're going to manipulate this equation to this one, and this is the time-independent Schrodinger equation with the harmonic oscillator potential inside of it. Why are we doing this? Here, here's the P operator. The basic idea is to factor the Hamiltonian. So here's the Hamiltonian. How are we going to factor this? If these were numbers, it would be easy. U squared plus V squared equals IU plus V times minus IU plus V. Here, however, it is not quite so simple because P and X are operators, and operators do not, in general, commute. X and P is not the same as P and X. Commutation problem. This is something you take for granted in standard, like, algebra that you learn from the age of 1 to 30 or whatever, or for your whole life. But now we have non-commutivity, which is throwing a wrench in the business. As we'll see in a moment, though you might want to stop right now and think it through for yourself. Why doesn't commutivity not work with these operators? Still, this does motivate us to examine the quantities. Boom. And here are the raising and lowering operators. They are ways of factoring this thing here. The factor in front is just there to make the final result look nicer. This factor, I'm assuming he's talking about. Well, what is the product of A minus and A plus? A minus and A plus, he does this, they work out, boom, you get this. As anticipated, there's an extra term involving xp minus px. We call this the commutator of x and p. It is a measure of how badly they fail to commute. In general, the commutator of operators A and B, written with square brackets, is, here's the commutator, is a new definition, and these are operators. The operator A, and then the operator B, minus the operator B, and then the operator A. In this notation, A minus, acting on A plus, is equal to this minus this, so minus the operator. So this thing he did here. Let me just stop for a second and talk about these operators. If this operator, momentum, is acting on the x, keep in mind the x operator is just x, but the momentum operator has a derivative with respect to x. So if you do momentum operator, then position operator, then psi, psi is being multiplied by the position operator, which is x, and then you take a derivative with respect to x. So you've added an extra x in the business, okay? If you do it the other way around, which is position operator, and then momentum operator, then your wave function psi, the position operator x is on the outside of the derivative. So first, you take a derivative of just the psi. This is why doing this, or sorry, doing x then p is not the same as doing p then x. In multiplication, this doesn't matter because 3 times 2 is the same as 2 times 3, right? But with operators, it is a bit different. So it doesn't matter, we got the commutator, this is introduced to us. We need to figure out the commutator of x and p. Warning, operators are notoriously slippery to work with in the abstract, and you are bound to make mistakes unless you give them a test function f of x to act on. At the end, you can throw away the test function and you'll be left with an equation involving the operators alone. In the present case, we have x, the commutator of x and p acting on this function. So we have the commutator, first is x, then is the momentum operator acting on f, minus first x acting on f, and then momentum acting on it. So we do all this math, we get this, and then we get I, h bar, and f of x. In this case, he just added this f of x and f of x here so that he can proceed with this algebra here, right? Keep in mind, x is literally just x, and p is the momentum operator p, which was mentioned here, all right? So he's trying to find how this operator, or how this commutator acting on this function changes the function, and all it does is it spits out this constant. So dropping the test function, which has served its purpose, we get the commutator of x and p is equal to I h bar. Why are we looking for this? Because we tried to find what this was, and then we got this thing here, the commutator. So he defines the commutator as this. Then he rewrites this whole equation using the commutator right here, and he wants to find the value of this thing. Now he found it, it's I h bar. So we're going to replace this whole thing with I h bar here, and the i's cancel and the h cancel, and we're left with 1/2, which is awesome. With this, equation 2.50 becomes this. So a minus and acting on a, these are just operators, so they have to act on something. But I'm just going to say a minus acting on a plus is equal to 1 over h bar omega, the resonant frequency, or the frequency of oscillation, the Hamiltonian plus 1/2, or the Hamiltonian is equal to h bar omega, all of this multiplied by a minus a plus minus 1/2. This is very interesting. So this is another way of rewriting the Hamiltonian with these raising and lowering operators. These raising and lowering operators we kind of created on our own. They're introduced here. The way we did it was by factoring this equation. Okay, nice. Evidently, the Hamiltonian does not factor perfectly. There's an extra 1/2. Boom. So we couldn't factor it perfectly. There's an extra 1/2 here on the right. Notice that the ordering of a plus and a minus is important here. The same argument with a plus on the left yields, boom. And in particular, the commutator of this and this is 1. Meanwhile, the Hamiltonian can equally well be written as this. So if minus is acting first on the left, technically you read this as this acting first, because your wave function or your test function is going to be on the right side of the operator. So the wave function first is acted upon by a plus, and then the result of that is acted upon by a minus. So if you do a plus, then a minus, there's a minus sign here. But if you do a minus, then a plus, there's a plus sign over here. So it's a little different. Commutator equals 1. I don't know if that's too important. In terms of a plus minus, the Schrodinger equation, 26, I'm not going to read this stuff right now. I'm just going to read the content. For the harmonic oscillator, takes the form, boom. So this is the Schrodinger equation, time-independent Schrodinger equation. We replace the Hamiltonian. In this case, the Hamiltonian includes the potential of the harmonic oscillator, which we introduced before. We factor the harmonic oscillator, and then boom, we get this, a new equation. Why are we doing this? Let's keep reading. In equations like this, you read the upper signs all the way across, or else the lower signs. So you see how here there's a plus and a minus, and here there's a plus and a minus and a plus. Minus is on the top, and here a plus and a minus. These are basically two equations. You can either take the plus here, the minus here, and the plus here, or the minus here, the plus here, and the minus here. So two different equations, just for the order, like organization, because we have two different equations here. Hope that makes sense. Now here comes the crucial step. I claim that if psi satisfies the Schrodinger equation with energy E, that is H acting on psi equals E psi, then A plus acting on psi satisfies this Schrodinger equation with energy E plus H omega. Therefore, H acting on A plus acting on psi is equal to E plus H omega times A plus acting on psi. Proof. Here's the proof. H is acting on A plus, then A plus is acting on psi, is equal to this. So we just replace this with what we have introduced before, or sorry, we replace this with what we have introduced before, and then we still have this left. We distribute everything here, Keep in mind the order of the distribution matters here, because if you switch A plus and A minus here, it's going to be different. So here you see A plus, A minus, A plus. This is because we have A plus, A minus, and it couples with this A plus. And here's the last A plus, which couples with this 1/2. Nice. Now we can factor out this A plus from the other side. So this A plus gets pulled out. It gets pulled out here, and it gets pulled out from here. Boom. It gets pulled out here. Boom. This A plus is left on the outside. This H omega goes on the inside. We have A plus, A minus, plus 1, plus 1/2. Boom. And this whole thing can be written as the Hamiltonian again. Then we have A plus here, E plus H bar omega psi. Okay, so this little proof just tells you that this is true. If this is interesting to you, you could look at it in more depth. I use equation 2.56 to replace A minus A plus by A plus A minus plus 1 in the second line. Notice that whereas the ordering of A plus and A minus does matter, the ordering of A plus and any constants such as H bar, omega, and E does not. An operator commutes with any constant. By the same token, A minus acting on psi is a solution with energy E minus H omega. And here's another proof for that. Here we have a cool picture of a cat climbing this ladder, and on the ladder we have these interesting symbols. The ladder of states for the harmonic oscillator. Here, then, is a wonderful machine for generating new solutions with higher and lower energies if we could just find one solution to get started. So we find one solution, and we apply these raising and lowering operators, and we find new solutions. But we still haven't found one solution, so we need to find the first one. We call A plus minus ladder operators because they allow us to climb up and down in energy A plus. In energy, A plus is the raising operator and A minus the lowering operator. The ladder of states is illustrated in figure 2.5. Here's figure 2.5. State psi has energy E. State, the one higher state, psi, when you raise it by 1, has energy E plus H bar omega. So this is the quantization of energy. Energies are only available in discrete packets, which are H bar omega units away from each other. You raise again, you get plus 2 H bar omega. You raise again, plus 3 H bar omega. From here, you lower, you apply the lowering operator, you get E minus H bar omega, and then boom, 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 all the way forever. Here, I mean, here you can go forever. You can raise to however much you want. But eventually you're going to get to state E0 where you cannot lower anymore because of the ground state energy. So I think he wants to find this solution here to work with. But wait, what if I apply the lowering operator repeatedly? Eventually I'm going to reach a state with energy less than 0, which according to the general theorem in problem 2.3, which we have not done yet, does not exist. At some point the machine must fail. How can that happen? We know that A minus is a new solution to the Schrödinger equation, but there is no guarantee that it will be normalizable. It might be 0, or its square integral might be infinite. In practice, it is the former. It occurs, there occurs a lowest rung, call it psi 0, right here, that's the lowest rung of the ladder, such that if you act with the lowering operator on psi 0, the lowest state, you get 0. We can use this to determine psi 0. That's awesome. So this is like a little deduction thing. We're going to use this to find what psi 0 is. Cool. So we basically apply the lowering operator on psi 0. We get 0. We move stuff around so that we get this differential equation. Then we can solve this differential equation. Easy to solve. Boom, he does the solution. Boom, some ln, some stuff, and we get an exponential. Psi 0 of x, the first solution of the Schrödinger equation, of the harmonic oscillator potential is A, the normalization constant, times this exponential, some constants, and x squared. So this is a Gaussian. We call this a Gaussian function if it's e to the power of minus x squared. We might as well normalize it right away. Boom, he does normalization. Here's the normalization constant, or this, technically invert it because you get 1 is equal to this. You solve for A and you get this. Or A squared in this case, then you solve for A and you get this. So this is the actual solution. If you plug this into the Schrödinger equation for the harmonic oscillator potential, it will check out. To determine the energy of this state, we plug it into the Schrödinger equation in the form of equation 2.58. Let's just check 2.58. This one here. So this modified Schrödinger equation, we plug the psi in there and we find energy. And exploit the fact that A minus acting on psi 0 is equal to 0. So E0 is equal to 1/2 H bar omega. This is the ground state energy of the quantum harmonic oscillator. Awesome. With our foot now securely planted on the bottom rung, the ground state of the quantum oscillator, we simply apply the raising operator repeatedly to generate the excited states, increasing the energy by h bar omega with each step. That's so cool. Psi of n is equal to an. This is the new normalization constant. We apply the raising operator n times. So if you want to find the first excited state, you apply it 1 time. If you want to find the 31st excited state, you apply the raising operator 31 times. Each normalization constant is different. And what do you apply this raising operator on? The ground state wave function, which is right here. And the E is here. So we already determined this, or I guess he gets it from somewhere. E of n is equal to n plus 1 times h bar omega, where an is the normalization constant. By applying the raising operator repeatedly to psi 0, we can in principle construct all the stationary states of the harmonic oscillator. Meanwhile, without ever doing that explicitly, we have determined the allowed energies. Super cool. Let's check the example. Actually, let's see what's after the example. We got a bit more stuff, a proof, ooh, some more stuff, and another example, and then the section ends here. So that was the bulk of what happened here, the raising and lowering operators. Feels confusing? No stress. Let's check this example. The example that I was looking at was right here. Find the first excited state of the harmonic oscillator using equation 2.62. Boom. Alright, so we have psi 1 is equal to a1. Raising operator acting on the initial wave function. We have all the stuff coming out from the initial wave function, these things, and all the stuff coming out of the raising operator, which is this. Boom. Here we have the stuff from the raising operator, a derivative with an x. Here is the ground state wave function. And then boom, he just solves it. He does x, boom, and he also does a derivative. And this combines. You know what? This is a little strange. Let's actually spend a bit of time figuring this out. So a1 comes from this, right? This square root on the bottom comes from the raising operator, right? Let's peep the raising operator. Here it is, raising operator is 1 over this stuff, and then minus IP plus m omega x, okay? We have that in our example. Minus I, and since we have another minus, minus p, then the I disappears, and we have h bar, and then the derivative with respect to position. So this is the momentum operator here acting. M omega x, and then here we have this as a constant. This constant comes out all the way here, so it doesn't really matter. This a comes out all the way here, but this square root gets changed a little bit. Something over here happens. What I'm confused about is this thing has to be distributed here and then here. You see what I'm saying? So first it gets distributed there, boom. And then we have x, well, m omega cancels with this a little bit and we change that, but we have an x over here multiplied by this function. Here we have an x multiplied by this function, so we see that. But then we distribute this onto the derivative. We have minus derivative of x with respect to this. The derivative of this brings down this factor in the front, and then we get this thing again, because the derivative of an exponential is just the exponential itself times the chain rule thing that pops out from here. But then how do you combine this thing that gets distributed here with this plus x times the function factor? It doesn't make sense to me. We can normalize it by hand. Boom, as so happens, a1 equals 1. I wouldn't want to calculate psi 50 this way, applying the raising operator 50 times, but never mind. In principle, equation 2.62 does the job except for normalization. Okay, so this is just an interesting thing that I'm getting a bit stuck on, but I guess I gotta work this out by hand. So anyway, here's the first problem. We apply this and we find the excited state psi 1, and Griffiths himself says, I don't want to do this 50 times for this, but never mind. So if you get asked to do this 50 times on the test, pray Griffiths is there with you in spirit. Let's keep reading. You can even get the normalization algebraically, but it takes some fancy work. So watch closely. We know that a plus minus times psi of n is proportional to psi of n plus or minus. So we have this equation formed, boom, with the cn factor here. and then boom, we get a dn over here. Okay, cn and dn. We're basically trying to find this normalization constant so we don't always have to normalize by hand. So he's trying to do this fancy footwork so that we don't have to do this. But what are the proportionality factors cn and dn? First note that for any functions f of x and g of x, we get this. So f star times this raising lowering operator acting on g is equal to the lowering raising operator acting on f star times g. So there's a kind of a flip-flop thing going on over here. In the language of linear algebra, a minus plus is the Hermitian conjugate or adjoint. This is smart, or very cool. Introduction of new stuff. Hermitian conjugate or adjoint. So it's like if you flip the signs here, boom, you could plug it into the star version of the other one and you get the same equality. Proof, boom. I'm not going to peep this proof right now. This is something I'm going to read on my own time. I'm not going to bore you guys with it. But if you want to look at it, boom, pause the video, take a look at this. In particular, here they're doing the same thing, I guess, flip-flopping. Let's actually read it a bit closely. A plus or minus acting on psi n, all of this complex conjugate. A plus or minus acting on psi of n, no complex conjugate. Boom. Then we factor out. Oh yeah, we do this flipping thing, so we can pull these guys out and put them in here. Except their signs flip because of this rule that we just saw. But invoking equation 2.58 and 2.62, I'm not going to check what those are. A plus acting on A minus acting on psi n is equal to n psi n. A minus acting on A plus acting on psi n is equal to n plus 1 psi n. Interesting. So he does all this. You know what, I'm just going to skip this. You guys can check it out if you want. But since psi n and psi n plus or minus 1 are normalized, it follows that cn squared equals n plus 1 and dn squared is equal to n. And hence, boom. Okay, so he basically took the raising lowering operator equations, did some fancy stuff with them to find out that the normalization factor is this over here. So if we have state psi n and we raise it by 1, apply the raising operator to psi n, we get psi n plus 1 and the normalization factor is square root of n plus 1. So from psi 0, we get psi 1, and we plug in 0 here. 0 plus 1 is 1, square root of 1 is 1. So the normalization constant of going from psi 0 to psi 1 is 1, and we saw that in the example right here. This is how we went from psi 0 to psi 1. So he just did this generally for all of us. So if we want to find psi 50, we could just apply 50 times. We don't have to find the normalization constant. We could just do this. Same thing with the lowering operator, except there's a square root and here this is normalization constant. Thus, psi 1 is equal to raising operator acting on psi 0. Psi 2 is equal to 1 over root 2 raising operator acting on psi 1, which is equal to 1 over root 2 raising operator squared acting on psi 0. Psi 3 is equal to 1 over root 3. Same thing with all the other ones. It's basically just this applied to the first 4 states. And so on. Clearly, we get psi n is equal to 1 over square root n factorial of, or multiplied by the raising operator n times, if we want to get to state n, acting on the ground state wave function, which is to say that the normalization factor in equation 2.62 is an is equal to 1 over square root n factorial. In particular, a1 is equal to 1, confirming our results in example 2.4, which I just showed you guys up there. As in this case of the infinite square, well, the stationary states of the harmonic oscillator are orthogonal. Boom, we get orthogonality, which is the same thing we saw in the infinite square rule. This can be proved using equation 2.66 and equation 2.65 twice, first moving a plus, then moving a minus. I don't want to go through the proving, guys. If you want to take a look at it, pause, check the equations there, try to prove it on yourself. This is very, very good practice. But for the purpose of just a lecture, I'm just gonna read the whole theory and not gonna spend much time on these proofs. So unless m equals n, then this must be 0. Orthonormality means that we can again use Fourier's trick, equation 2.37, to evaluate the coefficient Cn when we expand psi of x at t equals 0 as a linear combination of stationary states. This is super important and it applies to anything if you have orthonormal complete solutions. If it doesn't make sense, you got to do a bunch of problems, which we will try to do together. But just keep in mind that finding these coefficients Cn happens when you have orthonormal solutions and you use Fourier's trick and you expand the initial wave function in terms of these orthonormal basis wave functions. Very crazy. This is quantum mechanics, guys. What do you want me to say? So, as always, Cn squared is the probability that a measurement of the energy would yield the value En. Here we have another example, and that is the chapter. Let's actually just check the example really quick. Find the expectation value of the potential energy in the nth stationary state of the harmonic oscillator. Here's the solution. Expectation value of V, the potential energy, is expectation value of the operator, which is just this, which we saw from before. It's basically just an x squared with these constants. We apply this, boom, x squared is sandwiched inside psi star and psi n. We pull out the things here which don't depend on x, so they can be pulled out of the integral. There's a beautiful device for evaluating integrals of this kind involving powers of x or p. Use the definition equation 2.4a to express x and p in terms of the raising and lowering operators. Ooh, this is super useful. This example is super useful. Let's highlight it. Because instead of doing this integral, you can instead replace this x, in this case x squared, with this kind of thing, and it works out to be very, way more simple. In this example, we are interested in x squared, so we evaluate x squared. Basically square this whole thing. The square root gets removed. This thing gets squared, so you just expand it. X squared here. In this case, this one squared, and then plus this. Remember, the order of these matters. So a plus acting on a minus is not the same as a minus acting on a plus. So you cannot combine these. They are non-commutative. So V is equal to boom. We basically rewrite this, except we replace x with this thing that we have here, right? And we have all of these things. And these operators have to act from the left to the right. So first they act on this psi, not the complex conjugate. So you act on this one. You lower psi n twice. Here you raise psi n once, you lower it again. So you go back to psi n. Here you lower it once, you raise it once. You go back to psi n. Here you raise it twice. Whatever you get there, you just have 4 integrals you got to do, but the integrals should be pretty easy because of orthonormality. But a plus squared psi n is, apart from normalization, psi n plus 2, which is orthogonal to psi n. And the same goes for a minus 2 times psi n, which is proportional to psi n minus 2. So these terms drop out. We can use equation 2.6. That's so crazy. So look at this. If you raise this state twice, it goes from psi n to psi n plus, let's say we raise it first. It goes to psi n plus 1, psi n plus 2. Psi n plus 2 is orthogonal to psi n. So that integral disappears. If you lower it twice, it goes to psi n minus 1, psi n minus 2. Psi n minus 2 is orthogonal to psi n. So that integral disappears. So you basically just have to do these 2 integrals. Really cool. Or honestly, dope. So these terms drop out, and we can use equation 2.66 to evaluate the remaining 2. Boom, we evaluate it. He doesn't show it, it's left as an example to the reader. And we get this, which is the expectation value of this. Let's read. As it happens, the expectation value of the potential energy is exactly half the total. The other half, of course, is kinetic energy. This is a peculiarity of the harmonic oscillator, as we'll see later in problem 3.37. Alright guys, the next chapter, here we have a bunch of examples. These are going to take so long to do, I'll be real with you. If we just spend a whole video on each of these, you're going to learn a lot. But I kind of just want to go through the theory first. Next video, we're going to do the analytic method. Thank you guys for watching. I hope this was pretty fun. And let me know if you like these reading videos. Put it on 2 times speed, watch it or listen to it in the car. But drive safely. Thank you guys for watching. Peace out.